Hello, everybody. I am Akshay. This is Rodrigo, Clarissa, and Cameron, and we are HAND, or Hand and Neural Network Design. We are working with Dr. Tedeschi at the Humanoid Biorobotics and Smart Systems Lab, and our goal is to design an end-to-end neural network for speech control of a robotic hand. What this means is that we will have our circuit connected to a robotic hand with TCP muscles, and those are basically just plastic muscles controlled by voltage, and our controller should be able to control based on user interaction through speech input. So the user says close or for, and the hand should move accordingly. Mine and Rodrigo's part of the project is the software. We are working on the end-to-end network to do the speech control. An end-to-end network means that it takes in raw input and produces the output without any pre or post processing to the data. Right? For us, this means that we will be taking raw audio as the input without, for example, taking a transform of the audio and then outputting it to voltages for each of the 5 muscles. The 3 types of network we will be testing in terms of accuracy for sample data on human speech are a CNN, LSTM, and a GRU. A CNN, or convolutional neural network, is a feed-forward network, which means that each layer only depends on the past layer. An LSTM, or long short-term memory network, is a recurrent network, and it will take into account past, current, and future data, and will also store memory so that it can deal with sequences. And finally, the GRU, or gated recurrent unit, is like an LSTM, but a bit simpler because it doesn't store memory. It just looks at the previous output and the input. So using these 3 networks, we can compare the accuracy on human data. Now, Clarissa will talk about the hardware.
Yeah, so our circuit is designed to operate at a range of voltages, so it can work with a variety of the robotic systems that the HBS lab is designing. And it will take I2C output from the Jetson TX2 and feed it through an isolator and a digital to analog converter. The DAC has 8 output channels, and each of those will go to an amplifier that consists of an op-amp and a BJT to amplify both the voltage and the current needed to actuate the TCP muscles that we'll be using in our hand. And we'll also have a variety of voltage regulators, one of which will provide 3.3 volts to power the I2C isolator and 3.3 volts to power the DAC. The other 8 voltage regulators will have an output between 3 and 24 volts adjusted with a potentiometer, and that allows us to use different types of TCP muscles or different robotic systems. So all in all, we'll have 8 control channels, only 5 of which will be supported by software, but as mentioned, they can work with other robotic systems. And each of these will have input from the adjustable voltage regulator, an output from the DAC, an amplifier, and then an output with thermal and current fuses. And this will all be implemented on a custom 4-layer PCB.
Okay, any questions?
Any questions?
Yes, on the output to muscles, is that the robotic hand muscles?
Yes, so we're not designing the actual robot itself. The HBS lab has a mechanical team working on that. Our
Okay.
project is simply the controller. So we have the microphone, which is taking the speech to tell the hand what it wants to do. And then it'll process using our Jetson TX2, and then it'll convert that using our PCB into the actual motor inputs for the robot.
Okay, so you're just concentrating on output?
Yes, the controller.
Quantities and values and whatnot?
Mhm.
Okay,
So we're working on actuating the muscles, not designing the muscle itself.
okay.
Are you given a set of specifications of like what those actuations need to be already? So you're just mapping the speech to the, I'm assuming some sort of table of this command means these actual actuations.
That's where the network comes to play. Like we're trying to teach it basically what words would map to certain actuations of the hand, and from what we believe the hand doesn't have too many movements, so that we just trying to.
So the goal is to make it so that it's not a static mapping, right?
Yeah.
It's a network that can be trained to learn more commands in the future, for example, or to support a variety of commands or longer commands and things like that. So it's not just a static mapping where you do, for example, like a speech to text and then use that with a just a dictionary of commands.
Right. And from a hardware perspective, we haven't been given particular muscles that we're working with. So we'll get a 0 or 1 output from the GPU that says the muscle needs to be open or closed, and then we'll convert that with the adjustable voltage regulator and the DAC to be able to go to whatever voltage that muscle would need, whether it's 12 volts, 3 volts, 24 volts.
So are you creating your own vernacular for what words mean what things, and what actions?
Yeah, so for our training, we will be using whatever data we can gather. We'll start with simple commands such as open or free or something like that. And we can work from there depending on how our network is able to respond to that. With that, we are specifically going to train it on a few sample datas, a few sets of sample words so that we can get the hand to actuate, but it should have software support for any amount. If you have the data to train it, you should be able to support that with the network that we are designing.
What would that data look like, though? I mean, at some point, you have to be able to translate that this word means that it needs to be able to do this.
There are some, specifically with the CNN, we can use like a spectrometer view of the input, and that can be translated into kind of like this is what the word looks like, and this word should somewhat be like this output.
I think the question was, the data would have to be labeled, right?
Right.
Yeah.
So the data would have to have an associated, so it's supervised learning, meaning that it will have a correct answer.
Right.
The network will change its biases so that it will be closer to the correct answer the next time.
Right.
Okay, let's thank the team.